Hello students. So in this session we'll solve the solutions for the unit 5 assignment. We have solved some problems while we are dealing in our classes while the lectures were going on. At the time I have talked about some problems and there we used many concepts to address those problems. So let us try to solve these problems also so that you can get better idea regarding the topics of this unit. So as the first question says, a rectangular waveguide with some dimensions is given. So you should be careful to see that A is always greater than B. So that is the, until unless it is mentioned there, we always go with A greater than B. So the largest one is A. So I can see then A becomes 6 centimeters and B becomes 3 centimeters. And what it is not given anything here whether it is air filled or anything, but let us assume that it is filled with air. Then epsilon r is equal to 1 and mu r is also equal to 1. If that is the case, the question asks for, in order to have a single mode of operation, find the possible frequency ranges of operation such that the lowest frequency is 5% above the cutoff and higher frequency is 5% below the cutoff of the next higher order mode. So for a rectangular waveguide, if you think about it, so the first cutoff frequency occurs for TE10 mode, and the next cutoff frequency can either occur for TE20 mode or it can also happen for TE10 mode. So this mode can be either here or here, right? This it will be here if B, the dimension of B is less than a by 2, and it will be here if dimension of B is greater than a by 2. If B is exactly equal to a by 2, then it will be equal to the cutoff frequency of T. So you can see here B is exactly equal to a by 2. So I can say that the cutoff frequency of TE20 mode will be equal to the cutoff frequency of TE10 mode. I mean TE01 mode. So all I can say is we will prove that it will happen in fact, but the next higher order mode, right? The first mode, so the first mode is TE10 mode. So the next mode is the next higher cutoff mode is either TE20 mode or TE01 mode. So let us find cutoff frequencies of all these modes and see which mode will come after. Okay, so let us try to write the formula for cutoff frequency. If you remember, the formula for cutoff frequency is derived from this equation k square, kc square is equal to k square minus beta square, and where kc square right, so that is, and where we had the equation that of course kc square is nothing but m pi by a whole square plus n pi by b whole square. So at a frequency, the frequency at which k is exactly equal to kc square, or frequency at which k equal to kc, is what we call as cutoff frequency. So in place of k, if I put omega or 2 pi, the frequency fc times square root of mu and epsilon should be equal to kc square. So that is your cutoff frequency, but kc square is nothing but m pi by a whole square plus n pi by b whole square. Okay, so of course this whole square. So if I take a square root of it, I can see that 2 pi fc into the square root, I can write as square root of mu naught epsilon naught and square root of mu r and epsilon r is equal to square root of m pi by a whole square plus n pi by b whole square. I can bring pi out. Okay, I can bring pi square common and I can bring it out, so pi gets cancels out, and this can be written as 1 by c, velocity of light. So I can see now Fc is nothing but c by 2 times of square root of mu r and epsilon r square root of m by a whole square plus n by b whole square. So this is your formula for cutoff frequency of any mode, okay, whether it is TEMN mode or TM times of MN mode. For any common mode, this is the formula for the cutoff frequency, and this is the formula which I am going to use for this whole tutorial, right? So with that, so let me write A is equal to 6 centimeters and B is given as 3 centimeters, and the general cutoff frequency of any MN mode, right, is C by 2 square root of epsilon r into mu r times square root of m by a whole square plus n by b whole square. So in our case, if you assume it is air filled, if we take epsilon r is equal to 1 and mu r is equal to 1, then this becomes C by 2. So let us find the cutoff frequency of TE10 mode. So for TE10 mode, the cutoff frequency is C by 2 times of square root of 1 by a whole square plus 0 by b whole square. That gives me C by 2a. Okay, so if I put the values of C and a, right, I get an answer of 2.5 gigahertz. So this is the cutoff frequency of TE10 mode. So the next higher order mode will be, so this is TE10 mode. So the next higher order mode can be TE20 mode. So let me find the cutoff frequency of TE20 mode. So I have to put 2 by a whole square plus 0 by b whole square. This gives me an answer C by a, so which is 2 times of this, which is 5 gigahertz. I want the cutoff frequency of TE01 mode, so that is C by 2 times of 1 by a, sorry, 0 by a whole square plus 1 by b whole square, that is nothing but C by 2b, so that is 3 into 10 to the power of 8 divided by 2 into 3 into 10 to the power of minus 2, so which will be again 5 gigahertz, right? So I can see that at 2.5 gigahertz there is TE10 mode, at 5 gigahertz there is TE20 mode and as well as TE01 mode. So what I want is, in order to have a single mode operation, I have to operate in this band, and I want to have an operating frequency range for the lowest frequency. The lowest frequency should be 5%. 5% is 5 divided by 100. Okay, so it will be 0.05, right? So it should be 5% above the cutoff frequency. So if at all, if I take the lower limit is, then it is exactly equal to the cutoff frequency. So I want 5% more than what I have, so I have to take 5% more of it. So if I have cutoff frequency of TE10, then I have to take 5% of it and I have to add it again. So that much more I want. So it is nothing but 1.05 times of FC of TE10. So I have the cutoff frequency of TE10 2.5 gigahertz. So that makes the lower limit of my operating frequency as 2.625 gigahertz. So let's talk about the higher operating frequency. So the higher operating frequency is asked to be again 5% below the one. Okay, so the upper frequency, the higher one is the next one, which is TE01 mode. So out of this I have to decrease 5%, so I have to decrease 0.05 of it, so it is 0.95 times FC of TE10 mode cutoff frequency, 01 cutoff frequency, which turns out to be 4.75 gigahertz. So here, so I have my upper operating frequency and I have my lower operating frequency, and between these two frequencies I will be operating my uh, waveguide. Okay, so let's move on to the next question. So in this question, it is said it's an air-filled waveguide, rectangular waveguide, and the dimensions are given. So if it's air-filled, mu r and epsilon r is equal to 1, and then the electric field is given. So this is, it is said that it is the z component. Okay, and they are asking you for the intrinsic impedance of this mode. First of all, the question is whether it is TE or TM mode. As I can see, the z component is non-zero value. Okay, it cannot be transverse electric, it can be transverse magnetic only. So I can say Ez component is not equal to 0, that makes it a TM mode. Okay, and from the similarity, okay, I can see that m pi by a is equal to 2 pi by a, and n pi by b is equal to 3 pi by b. So that makes m is equal to 2 and n is equal to 3. So this implies this mode is a TM23 mode. Right, so because, and of course from the expression this looks like cos of omega t minus beta z. So this makes omega is equal to 10 to the power of 12. That makes the frequency of operation 2 pi f is equal to 10 to the power of 12. So that makes frequency is equal to 10 to the power of 12 by 2 pi, that is 159.15 gigahertz. So that's your frequency of operation. So let us try to find what is the cutoff frequency of this mode, just to see whether this mode can propagate or not. So the cutoff frequency of any mode, the formula is like this: c by 2 times of square root of mu r and epsilon r, which is 1, so I will not write it. Okay, divide into square root of m by a whole square plus n by b whole square, and this is the cutoff frequency of TM23 mode. So you put a 2 here and you put a 3 here, and we have the values of a and b, right? So if you substitute those values, you will end up with an answer of 15.81 gigahertz, which is definitely lower than the cutoff frequency. Means the operating frequency is more than the cutoff frequency, so this mode can propagate, and it is propagating. So now if I want the wave impedance, so because this is a TM mode, the wave impedance for TM mode, so in the question I guess I have accidentally asked it as intrinsic impedance, so this wording is not right. So you need to calculate the wave impedance, right? Intrinsic impedance is zeta, so my wording is wrong, please correct the question. So for the TM mode, the wave impedance is given as beta eta by k, right? So if you put beta as square root of k square minus kc square times eta by k, and because it is free space, eta is nothing but eta naught, and eta naught is nothing but 120 pi. So 120 pi times of, and for the square root, if I take k inside, I get square root of 1 minus kc square by k square. I can write this by expanding, I get fc by f whole square. So I have the value of fc and I have the value of f. If I put them here, I get the wave impedance as equal to 375.12 ohms. Right. So that is how we calculate this. Let's move on to the next one. So the question asks for when the dominant mode is propagated in an air-filled waveguide. So the dominant mode is definitely TE10 mode and it's air-filled, so mu r and epsilon r is equal to 1. The guided wavelength is given. So the guided wavelength is given as 4 centimeters and the frequency of operation is given as 9000 megahertz. Okay. So the question asks for what is the breadth, means they are asking what is the value of A. So because it's a dominant mode that is traveling, so we know that the cutoff frequency is given as C by 2 times of square root of 1 by A whole square plus 0 by B whole square, which gives me the answer C by 2A. If the FC is C by 2A, then lambda C is nothing but C by FC, right? Because it's free space, it is simply C, so you get 2A. So I have the expression for lambda C. So we have an equation that kc square plus beta square should be equal to k square. I can write kc square as 2 pi by lambda c square, and for the in the waveguide, beta is its propagation constant and its corresponding wavelength is we call as guided wavelength lambda g, and for a wave without any bounds the wavelength we call as 2 pi by lambda whole square. So from here I can write the equation that 1 by lambda c square plus 1 by lambda g square is equal to 1 by lambda square. So I have lambda c. For lambda c it is nothing but 2 by a whole square. And what is a lambda? So frequency is given, lambda is c by f, so that is 3 into 10 to the power of 8 divided by 9 into 10 to the power of 3 into 10 to the power of 6. You get this as 1 by 30, and so if I put 1 by 30 in the lambda, okay, then I will get, and lambda g is also given, which is 4 centimeters. If I use all those values, from there I can calculate the value of A. I get it around 3.15 centimeters, right? So that is how you solve this problem, right? So let's move on to the next one. So for the dominant mode they are asking you, they are saying it's an air-filled wave, rectangular waveguide, and for the dominant mode they are asking you to find the cutoff frequency. So the cutoff frequency for TE10 mode is, we saw previously, we got that is C by 2A, right? So we can write this as 3 into 10 to the power of 8 divided by 2 into 4 into 10 to the power of minus 2. You get it around 3.75 gigahertz. So this is the cutoff frequency for an air-filled dominant mode. So they're asking you to find the wave impedance for TE10 mode. So this is A part. So B part is they want wave impedance for TE10 mode and wave impedance for TM11 mode. So for T mode it is k eta by beta, because it's free space air filled, I can take eta naught, so that is 120 pi divided by square root of 1 minus fc by f whole square, right? Because beta you can write as square root of k square minus kc square. From there I have derived this formula, right? And for the same way, for TM mode it is beta eta by k. Okay, we get 120 pi times of square root of 1 minus fc by f whole square. So this fc is for TE10 mode and this fc is for TM11 mode. So let us find cutoff frequency for TE10 mode for this waveguide dimensions. So that is c divided by 2a, which is 3 into 10 to the power of 8 divided by 2 into 7 into 10 to the power of minus 2, right, which is 2.142 gigahertz. Let's find the cutoff frequency of TM11 mode. So for TM11 mode it is c by 2 times of square root of 1 by a whole square plus 1 by b whole square. So I have the value of a, I have the value of b, and I know the value of c. If I put it here, I get the answer to be 4.791 gigahertz, and the operating frequency is taken as 6 gigahertz. So if I substitute all these values here, the FC is here, F is here, and 120 pi, right, you will get an answer for the wave impedance of TE01 mode as 403.58 ohms, and for TM11 mode you need to get an answer of 226.94 ohms, right? So that's how you do it. So I'll move on to the next problem. So in this problem, again, it's a lossless air-filled waveguide. So epsilon r and mu r equal to 1, and it's operating in some band of frequencies, and the A is given and the value of B is given, and the dominant mode is propagating. So TE10 mode is propagating in Z direction, and the operating frequency is given as 3 gigahertz. So they are asking what is the power that is transmitted through the waveguide if the excitation level of electric field, if the magnitude of the electric field is 10 kilowatt per meter. So we know the total power that is transmitted is the magnitude of electric field square divided by 4 times of ZTE10 mode, wave impedance of TE10 mode, times the area A into B. So let's find first the cutoff frequency of TE10 mode. Why do you want the cutoff frequency? Because the ZTE10 is nothing but k eta by beta, eta naught because it is air filled, is equal to what I'll get. So this is nothing but 120 pi divided by square root of 1 minus cutoff frequency of TE10 divided by frequency of operation whole square. So I have the frequency of operation, but I need the cutoff frequency here. So what is the cutoff frequency for TE10 mode? Is nothing but C by 2A. So it is 3 into, because it's free space, it's air filled, so 3 into 10 to the power of 8 divided by 2 into 7.214 into 10 to the power of minus 2. You get it around 2.079 gigahertz. So once I have the cutoff frequency and I have the operating frequency, so I can find the value of the impedance, which is 377.89 ohms. So once I have the power transmitted is nothing but 10 into 10 to the power of 3 whole square divided by 4 into 377.89 into 7.214 into 10 to the power of minus 2 into 3.404 into 10 to the power of minus 2. So if you solve this, you get an answer of 162.453 watts, right? So that's how you solve this. Okay, so let's move on to the next one. So in this, again, the waveguide is said to be air filled, so it is mu r and epsilon r values are equal to 1, and the electric field expression is given, and they are asking you to calculate what is the vector magnetic field and as well as the phase velocity. So here, first of all, if you look at the standard format, it looks like the complete electric field vector is given and the electric field has x component, okay, and the wave propagation, I can see there is e power minus j beta z, so there is like e power minus j beta z, so it is a z direction propagation. And here from this I can say beta is nothing but 40 pi by 3 and omega is unknown, we don't know. So because this electric field, the wave is traveling in z direction, we right now don't know whether this is a TE mode or TM mode, right? But all I can we means we know what kind of mode it is. Definitely we can know the kind of mode it is, because I can see that the electric field has only x component. That means your electric field does not have z component, so Ez component is equal to 0. So if Ez is 0, if you can make Hz also go to 0, then you know you have a transverse electromagnetic wave, TEM wave, which cannot propagate in a rectangular waveguide. So Hz cannot be equal to 0. If Hz is not equal to 0, then what kind of mode it is? Then these are nothing but transverse electric modes. So this is a transverse electric mode, okay. And so from the looks of it, so for a transverse electric mode, so there is only 2 pi y dependency. Okay, and there is, so what is the mode number, we need to look into it. So here this is not the value of n. No, it's not the value of n. All I can say is usually you have m pi by a times of x and n pi by b times of y. So from the looks of it, from the equation, right, if I try to write this equation in phasor format, what I can see in the phasor format, the electric field looks like this: cos of 2 pi y times e power minus j 40 pi by 3 z times x cap. So I can say that n pi by b is actually 2 pi, and m pi by b is not there, which is equal to 0. Okay, sorry, m pi by a is equal to 0. So if the dimensions were given, maybe I can estimate what is the value of n here, which I am looking here. But all I can say is right now the m value is 0, but the n value is still unknown. Right. So how do I calculate uh, the frequency here as well as the magnetic field vector? So first let us try to calculate the kc. Kc square is nothing but m pi by a whole square plus n pi by b whole square. So that means 0 square plus 2 pi whole square, that makes kc equal to 2 pi. But k square is nothing but beta square plus kc square. So beta is given as 40 pi by 3 whole square plus kc is given as 2 pi whole square. So that makes k square as, or k, this makes from this I get k equal to 13.482 pi. Okay, and from here, because k is nothing but omega into square root of mu naught epsilon naught, because it is air filled, from here I can get the value of omega. So we get the value of omega as 12.706 into 10 to the power of 9. Right, so this is the value of omega. So let me write this. I got the value of omega as 12.706 into 10 to the power of 9. So I have the value of omega. So let us try to find, so next what we have to do is we have to find the magnetic field vector. So how do you find the magnetic field vector? So there is only one way to do it. That means one of the way, or the most easiest way to do is to use our phasor formed Maxwell equations. Okay, so from the Faraday's law you can write that the curl of electric field is equal to, so I can write this, so the curl of electric field is equal to minus j omega mu naught, because it's free space, times h bar. So I have the value of omega, I know the value of mu naught, so this is known entity. So all you have to expand this curl. So you have x cap, y cap and z cap, dou by dou x and dou by dou y and dou by dou z, times your x component. So it is, say, ex component, there is no y and z components. So this becomes, this is your ex component, so this is ex. Okay, so I can see if I expand this curl, I get an equation like this: minus y cap minus dou ex by dou z plus z cap times minus dou ex by dou y should be equal to minus j omega mu naught h bar. So if I take with respect to z derivative, I get minus, so minus and minus it converts into plus, so you get minus y cap times, of course you get minus into minus, you get a plus, but with for dou by dou z you get minus 40 pi by into j times cos of 2 pi y into e power minus j 40 pi by 3 z plus z cap times, you have to take derivative with respect to y. For cos it is minus sign, so you get sine, so it is, so for with respect to y it is 2 pi sine 2 pi y e power minus j 40 pi by 3 z times of x cap. Okay, this whole thing should be equal to h bar, so I can see that for the h bar there is only z component and x component. So if I can bring this minus j omega mu naught this side, I get the final answer like this, which looks, so I can, let me write the final answer for h bar. So the final answer looks like h bar is equal to 1 by omega mu naught 40 pi by 3 cos 2 pi y e power minus j 40 pi by 3 times of z times y cap plus 2 pi j by omega mu naught sine 2 pi y e power minus j 40 pi by 3, right, times x cap. So this is your magnetic field expression. So once I have the electric and magnetic fields, how do I find the phase velocity? The phase velocity is always omega divided by beta. So in my case omega is 12.706 into 10 to the power of 9 and beta is 40 pi by 3, so I get an answer of 3.033 into 10 to the power of 8 meter per second. So this is how you solve this question, and this is your answer. So let's move on to the next one. Right, so a rectangular, again a rectangular hollow metallic waveguide is given. So as it says it's hollow, we can assume that it is filled with nothing, or mu r and epsilon r is equal to 1, and the dimensions of the waveguide is given, and the operating frequency is given as 10 gigahertz. So they are saying if the waveguide wants only T10 mode operation, so what is the cutoff frequency? So what is the, calculate the cutoff frequency for this waveguide mode, and also the guided wavelength is asked. Okay, so let us try to find it. So the cutoff frequency here is for T10 mode, the cutoff frequency is C divided by 2A. So it is 3 into 10 to the power of 8 divided by 2 into 2.29 into 10 to the power of minus 2, so which is 6.55 gigahertz. So what I want is the propagation constant beta. So because, of course I can also go in a different way, that we know that 1 by lambda g square plus 1 by lambda c square should be equal to 1 by lambda square. Because it's a T10 mode, lambda c is nothing but 2a. Lambda c is 2a because cutoff frequency is c by 2a, and lambda g is what we want. So 1 by lambda g whole square plus 1 by 2a whole square is equal to 1 by lambda square. So this is f is equal to c by lambda is equal to 10 into 10 to the power of 9. So from here I can say that 1 by lambda is nothing but equal to 10 into 10 to the power of 9 divided by c. Okay, so c is nothing but 3 into 10 to the power of 9, so I get 10 by 3. So I can write 1 by lambda square is nothing but 10 by 3 whole square. Okay, so let me use these values. So I have this 1 by lambda g whole square is equal to 10 by 3 whole square plus 1 by 4 into 2.29 into 10 to the power of minus 2 whole square. Okay, I mean I get the minus sign here. So let me do it. 10 divided by 3 square minus 100 divided by 4 into 2.29 square. Oh, sorry. So this is not 4, this is 2 into, my bad. So here I think made a mistake that c by lambda is 10 to the power of 9 and 1 by lambda is 3 divided by c. I think for c I have written 10 to the power of 9, it is actually 10 to the power of 8. So you get a 10 in the numerator again. So 1 by lambda is actually 100 by 3, so 100 by 3. So if I substitute this, I basically end up with a value of lambda g, which is around 3.97 centimeters. So this will be the guided wavelength. So this is your first bit A. So let us move on and do the next bit. Okay. So for the next bit, what other modes can propagate through this waveguide? So after TE10, the next higher order modes are either TE20 or TE01 modes. So let us check the cutoff frequency for TE20 is C by A. So that makes the cutoff frequency as 13.10 gigahertz, and the cutoff frequency for TE01 mode is C by 2B. So that is 3 into 10 to the power of 8 divided by 2 into 1.02 minus 2, which gives you 14.7 gigahertz. So as you can see, these frequencies, because your operating frequency is only 10 gigahertz and these are very much, your operating frequency is less than the cutoff frequency of TE20 or TE1001. So no higher order modes will propagate, only TE10 mode will propagate. And say for example, if we take a special case, so they are saying if you take a special case where A is equal to B, so it's a square waveguide now. So what modes can propagate? So when it is a square waveguide, then TE01 and TE10. So these are the degenerate modes. Right, these are all modes with same cutoff frequency. Right, so the other set is like TE11 and TM11, and of course the other set is TE21 and TE12 and TM21 and TM12. Right, so these are all degenerate set of modes. We can write so on. There are many degenerate because it's a square waveguide. So what will be the cutoff frequency of TE01 is equal to the cutoff frequency of TE10, which is nothing but C by 2A, which we got previously, that is 6.55 gigahertz. Okay. Now what we want to see, of course, there is another mode I forgot right here. So there is TE20 and TE02. Right, both kind of have the same cutoff frequency. So the cutoff frequency of T20 and T02 is again basically C by A, which is 13.1 gigahertz. So let us find for the cutoff frequency of the next higher order mode. So that is the cutoff frequency of TE11 or TM11 is nothing but C by 2 square root of M is 1 and N is also 1, but because it's a square waveguide, B is also equal to A. So this is nothing but C by 2A times square root of 2. So which we get as 9.263. So you can see now this frequency is, your operating frequency is greater than this cutoff frequency of TE11 and TM11 modes. So in this scenario, TE11 and TM11 modes also propagate. We can also find the cutoff frequency of this set. We get this answer as around 14.64 gigahertz. So you can see these are the modes. So these won't propagate, these won't propagate, but these modes can now propagate on the square waveguide when A is made exactly equal to B. Alright, so let's move on to the next problem. So this question is about a circular waveguide, an air filled, so a lossless air filled circular waveguide. So mu r and epsilon r is equal to 1, and the inner diameter is given. So A is given as 3 centimeters, and the operating frequency is given as 14 gigahertz. And they are saying that a TM11 mode is propagating, and they want you to find the cutoff frequency, guided wavelength, and wave impedance. So first of all, to find the cutoff frequency, let's try to find the cutoff wave number. So the cutoff wave number, the formula is either P dash Nm by A, or it is P dash Mn, P dash, simply P Nm by A. So depending upon what mode it is, you need to use that particular table. So because it's a TM mode, as we have already seen on our classes coursework, so this table is for TE modes, and whereas this table is for TM modes. So for the TM mode, because it's cutoff frequency of TM11 we want, so we want 1 1. So we are wanting N is equal to 1 and M is equal to 1. So first order, first root. Okay, so this is what we want. So that is 3.832 divided by A. So because the value of A is given, which is 3 centimeters, I can put it here. I get the value of Kc equal to 127.733. So when K is equal to Kc, that is when you have the cutoff frequency. So cutoff frequency is nothing but 2 pi square root of mu naught epsilon naught Fc is equal to 127.733. So from here I can get the value of cutoff frequency as 6.098 gigahertz. So once I have the cutoff frequency, what I want to find is beta. Okay. Okay, before finding beta, let us try to find what is the value of k at this operating frequency. And the operating frequency is 14 gigahertz. What is the value of k? So k is nothing but 2 pi frequency, that is 14 into 10 to the power of 9 into square root of mu naught epsilon. So this answer will be 293.215. But beta square is nothing but k square minus kc square. I have the kc square, I have the k value. So if I take a square root, I get the value of beta as 263.9393. So from here, beta can be written as 2 pi by lambda g, right? So this becomes equal to 2 pi by lambda g. So that gives us the guided wavelength as 2.38 centimeters. So once we have the guided wavelength, we have the cutoff frequency and guided wavelength. So the last thing to find is the wave impedance. So because it's a TM11 mode, the wave impedance is like beta eta by k, and it is free space, so you have eta naught. So that makes this as 120 pi times of square root of 1 minus fc by f whole square. So I have fc value here and I have the frequency value. If I substitute there, you will end up with an answer of 339.35 ohms. And that is how you solve this problem. Right, so let's move on to the next one. So in this question, if you see that the question asks for find the inside diameter. So A is unknown here, and it is a lossless and air-filled waveguide, so mu r and epsilon r are 1, and they are saying TE11 mode is propagating and the operating frequency is given as 10 gigahertz, and they gave us a thing that the cutoff wavelength of this mode, so lambda c of TE11 mode, is basically 1.3 times the operating wavelength lambda. So let us find the operating wavelength is nothing but 1.3 c divided by the frequency of operation. So I have c and I have f. I'll get an answer of 3.9 centimeters. So from here, what is the value of kc? Kc will be 2 pi by lambda c, which is nothing but 161.107. So once I have the value of kc, because it's a TE11 mode, so as I told previously, this is the table which you need to for TE. So kc of TE11 mode is nothing but the 1/1 root divided by a. So n is equal to 1 and first root, which is 1.84. So it is 1.841 divided by a is equal to, we have the value of kc, which is 161.107. So from here I get the value of a. So I get a is equal to 1.142 centimeters. So that is how you solve this problem. Right, so let's move on to the last one. So in this question, it's a question for parallel plate waveguide, and for this parallel plate waveguide, the distance between the plates is given that d is equal to 1 centimeter, and they are saying it is filled with a dielectric medium whose epsilon r is 2.1. So they want you to determine, as you know, that the lowest from 0, the mode that travels, the dominant mode is TM mode. So they want to operate it as a TM mode propagation. So the higher order mode, the first higher order mode will be TE1 mode or TM1 mode, and after that you get the next higher order modes. Okay, of course, these are the higher order modes that you will see. So in order to have only TM mode propagating inside your waveguide, so this will be your highest operating frequency. So for that, you need to get the highest operating frequency, we need to know what is the cutoff frequency of TE1 mode or TM1 mode, right? So for these modes, the cutoff frequency is m pi by d. So here the m value is 1, so it is simply pi by d. So we have the value, but for this kc of t, the wave number of t1 or tm1 is m pi by d, because m is 1, so it is pi by d. So if you, when k is exactly equal to kc, that is your cutoff frequency. So if I write the cutoff frequency 2 pi fc times, because there is a dielectric medium now, okay, you should be careful, because now you have square root of not mu naught epsilon naught, and you also have square root of mu r is 1, but there is epsilon r, okay, is equal to pi divided by d. So we can write this square root of mu naught epsilon naught as 1 by c. So from here I can write fc is equal to 3 into 10 to the power of 8 into 2 into square root of epsilon r, right? Pi gets cancels out, divided by 1 by 10. D is 1 centimeter, so 10 to the power of minus 2. So you get an answer of 10.35 gigahertz. So you can operate it with the TM mode operation till 10.35 gigahertz. After that, higher order modes will come into picture. Okay, and the question asks for also find the range of frequencies over which T and TM11 modes and no other higher order modes will propagate. So they're asking you after, so the next higher order modes will be TE2 or TM2 modes. So for that to happen, the KC should be TE2, right? So if, to get that, you basically have to have KC2, right? So that then M is taken as 2, you get 2 pi by d. So in the same formula for the cutoff frequency, you get a 2 here. Okay, so if there is a 2 here, you get a 2 here. So the next so this will be the cutoff frequency of TE2 TM2 will be simply 2 times of this, which is right, which is 20.7, right, something 20.7 gigahertz. So till 20.7 gigahertz, what modes can propagate is TM, TE1 and TM1 can propagate, but after that even higher order modes like TE2 and TM2 can also come into picture, right? So that is how you can solve this question. So that ends our solutions to our tutorial. Thank you.